Guys, welcome back. Hope you had a great weekend. So today we are going to take a look at two body problems. So in these problems, we are going to be looking at the motion of two objects in respect to one another. So we are just going to delve right in with an example. And again, in two body problems, we are looking at the motion of two objects. So in this first example, we have car 1 and car 2 1,000 meters apart. Car 1 travels 30 meters per second north, and car 2 travels 45 meters per second south. Our goal is to find where the cars will meet. So a good starting point for these problems is to kind of sketch your motion. What is your position versus time graph going to look like for the motion of each of these cars? Okay. So if you read the problem, we know that car 1 is traveling north and car 2 is traveling south and starting 1,000 meters away. Okay, so since car 1 is traveling north, it might be a good idea to have this car start at the origin. Okay, make it easy on ourselves. And then have north be the positive direction. Car 2, however, we know is going to start 1,000 meters away. So if car 1 starts at the origin, car 2 is going to have a y-intercept of 1,000. Okay? The other thing to keep in mind here is that car 2 is traveling in the opposite direction. So if car 2 is traveling in the opposite direction, we need to show that in our graph by having a slope of opposite sign. Or here our slope is going to be negative to show that car 2 is traveling south. Since it's traveling at a faster rate, our slope for car 2 is going to be a little bit steeper than what we saw for car 1. Okay. Our end goal is to find where the two cars will meet. So what is this position right here where our two cars intersect? Okay. So a good place to start off with these is once we have kind of a sketch of what our motion will look like is to write an equation for each of our cars. So if we look at car 1, okay, to find our position, or y, we're going to want to take our slope, and remember our slope is equal to the speed of the car. So for our equation for car 1, we're going to have a slope of 30 meters per second times our x variable, which in this case is time. Since car 1 starts at the origin, we're not going to have a y-intercept for this guy. However, looking at car 2, we're again going to write an equation for this line where we have our position, our y variable is equal to our slope. In this case, we can see car 2 is traveling in the opposite direction. So we need to make sure that to show that that slope is negative. And in this case, car 2 is traveling with a velocity of 45 meters per second south. So our slope here is going to be negative 45 meters per second times our x variable time plus our y-intercept. If we look at car 2, he starts 1,000 meters away. So we're going to show that by having a y-intercept of 1,000 meters. All right, so once we have a sketch of what our graph or what our motion looks like, we can then write an equation for the motion of car 1 and its position as a function of time and car 2. So notice we have two separate equations for car 1 and car 2. Our end goal is to find where the cars will meet. Something we need to keep in mind here that's important is that when the cars meet, that means their position will be the same. Okay? So since when they meet, they have the same position, our y variables for either equation will be the same. So we can actually set these two equations equal to one another. So we have our equation for car 1, 30 meters per second times time, and we can set that equal to our equation for car 2. Negative 45 meters per second times time plus 1,000. From here, it just becomes algebra, okay, in order to solve for the time. So first we'll find out when our cars meet. So we'll add 45 to either side, and we'll end up with 75 times time is equal to 1,000. And we'll find that our cars will meet after 13.33 seconds. Okay. So that tells us the time that our cars will meet. But remember, our end goal is to find where they meet. So once we have the time, what we can do is plug that back in to either one of our expressions to find what position our cars will have at that time interval. It does not matter which equation you plug that time into because our positions are the same. So we can just use the equation for car 1. We choose their position is equal to 30 meters per second times our 13.33 seconds. And we'll find that our cars will meet at a position of 400 meters from the origin. It's always good to give a frame of reference of where you're measuring from. So here we'll find our cars will meet at a position of 400 meters from the origin. Okay. So when you're looking at two different objects, you want to sketch your motion first. Then we'll come up with an equation for car 1 and car 2. There are two objects in motion. And then since we want to find where our cars will meet or where their positions will be the same, we can set those two equations equal to one another to solve for time and then plug that time into our position equation. Let's take a look at another example. In this example, Sam and Alex are racing. They leave from the same position, but Sam has a 5-second head start. If Sam is running at a constant speed of 7.28 meters per second, and Alex is running at a speed of 9.55 meters per second, we want to see at what time will Alex pass Sam. So for this one, same thing as in our last problem, always a good idea to kind of sketch out our motion first. What will our two objects look like in our position versus time graph? What is different about this one is that they start at the same position. So since both of our objects are starting at the same position, it's easiest to just have them start at the origin. Make it easier on yourself. All right. So in this case, Sam has a 5-second head start. So that means Sam is going to start running first. So we're going to have Sam start running at time 0. Okay. So Sam has a 5-second head start. Starts running first. So we're going to have them start running at time 0. Okay. And then since they're only moving in one direction, we're just going to have them move in the positive direction. Okay. Alex, however, is going to start after Sam. Since Sam had a 5-second head start, Alex is going to start 5 seconds later. So if Sam started at time 0, that means Alex is not going to start until time of 5 seconds. If you look at this, Alex is running at a quicker speed, so that means their slope is going to be a bit greater. So when we draw this, we want to draw Alex's slope to be a little bit steeper than Sam because they're running at a quicker pace. All right. So in this problem, we have our objects start at the same position, so we both have them start at a position of 0. However, they do not start at the same time, so we need to show that Alex starts 5 seconds later by having them start at a time of 5. Once we sketch our motion, we are going to follow the same process that we did in our previous equation, or previous example. We are going to write an equation for Sam and Alex's motion. All right, so if we look at Sam, have our position, our y, is equal to our slope, which we know is equal to our speed. If we look at Sam, they have a speed of 7.28 meters per second times time. Okay. And since we start at the origin here, we don't have a y-intercept. Alex, when we look at his equation, we again have our position equal to our slope. Remember, that's the same thing as our speed, so 9.55 meters per second. Notice how since they are running in the same direction, we're going to say both slopes are positive. So since they are both running in the same direction here, those slopes are going to have the same sign. What is different though is that Alex starts 5 seconds later. We need to show that in our equation. So what we need to show is that Alex is running 5 seconds less than Sam. Okay? Since they start later, they're going to be running for less time than Sam. So since they are running for less time, how we are going to show that in our equation is instead of just multiplying our slope by time, we instead are going to multiply it by time minus 5 seconds. Okay, and we need to put that in parentheses because that whole quantity right there represents the time that Alex is running. Okay, so to show that Alex is running for 5 seconds less than Sam, we need to do this t minus 5 in parentheses because they leave 5 seconds later. Okay. Once we get to this point, we want to find at what time their positions will be the same. And since we want to find where their positions are the same, we can set our two equations equal to one another. So our 7.28 times time is equal to 9.55 times minus 5. This one, we're going to have to distribute the 9.55 because we're multiplying it by a quantity in parentheses. So when we simplify this, we'll get 7.28t is equal to 9.55t minus 47.75. And from here out, it again just becomes an algebra problem. So we can subtract 9.55 from either side and then divide, and we'll find that they're going to pass after a time of 21.04 seconds. Okay, and keep in mind, we're considering time 0 to be when Sam leaves. So they need 21.04 seconds after Sam leaves. If we wanted to find what position they meet at, we again could just plug that time into either one of these equations. It does not matter, since when they meet, they will be at the same position. So we could just do 7.28 times our time at 21.04, and we should find that they meet at a position of 153.14. Okay, so it's super important that when you have these questions where they're starting at different times, that you always subtract the delay. So always subtract how much later your second person is leaving by. Okay, and that's super important because then you're not saying that they're running for more time than they are. We need to show that Alex is running for 5 seconds less. Okay. All right, I hope this helps. Please let us know if you guys have any questions. Otherwise, hope you have a great day.